time for me to be in this beautiful country. So let's talk about my lectures. The aim of these lectures is to give an introduction to supergravity, a general introduction to supergravity, and to its mathematical formulation, in particular to gauge supergravity. Okay? I would like to give you a kind of taste of what are the mathematical structures occurring in these theories. I thought it better to give a preliminary slide presentation, okay, because I thought that maybe not everybody in the audience is familiar with the exterior formulation of general relativity, field line formulation, and all these things. Okay, so I thought it better to give a preliminary presentation on a slide presentation, and in which I set the stage, okay, for the subsequent lectures, and I fix also the formalism, okay, the notation and everything. So let me give first an outline of this talk. I'll give it here, of these lectures. Outline. So I will give this, let's go to 0, preliminary presentation. Okay, then I will discuss, give a introduction and motivation, general motivation. 2, I will deal with review the general features of engaged supergravities. Supergravities. Duality. Structure of these theories, where by duality structure I mean global symmetries. The global symmetry is a peculiar feature of these engaged supergravities and makes them particularly appealing, okay, as theories. And then I will move to gauge supergravities. Gauge supergravities, okay, and I think it's going to be tomorrow. Okay, we're going to start dealing with gauge supergravities tomorrow. So the general formulation. Okay, so the general ideas and gauge supergravities, and what should I do here? Formulation of the gauging procedure. Six, duality covariant formulation. Covariant. Of gauge supers and embedding them. Then I will touch upon the topic of tensor hierarchies, which follows from this formulation, naturally follows from this formulation. gauged maximal supergravity talk about gauge maximal supergravity. And if I have time, I will discuss in detail some examples of dimensional reduction, okay, which generalize the ordinary, well, the trivial dimensional reduction on a torus, because it contains some fluxes or some non-trivial internal geometric structure of the manifold, like the Church-Schwartz compactification. I will review, if I have time, okay, and show how them lead to a gauge supergravity in lower dimensions. So, examples of dimensional reductions with fluxes. So here we will see how gaugings, that is internal existence of an internal local symmetry, follows from dimensional reduction in the presence of fluxes. Okay. Okay. So this is roughly speaking the outline of the course. Let's start from the preliminaries. Okay. So let's start with some references. These are the main references on the general subject of supersymmetry and supergravity. They are very well known references. Okay. While for the specific, for the specific subject of gauge supergravities or dualities in a gauge supergravity, so for the specific subjects of which will be dealt with in this course, okay, I can suggest these references. Okay, the first is the lecture notes, which should be available. To you on the website, and then these are recent reviews on the subject. Okay. Please, if you have any questions, don't hesitate to stop me and ask. So let's define what we are talking about. So what is supergravity? I guess many of you should know the basic notion of what supersymmetry and supergravity is. So supergravity is a field theory which is invariant under Lotto, that is space-time dependent supersymmetry transformations. Okay. Now I think I have little to add to what Sam said yesterday as an introduction to supersymmetry. It was a very nice introduction. So I just have very few things. I just recall that supersymmetry is a symmetry between bosons and fermions. It relates bosons and fermions. Acting on a bosonic state gives you a fermionic state, and acting on a fermionic state gives you a bosonic state. And therefore, it associates with each particle a superpartner with a different spin statistics. Now, in order to do so, then of course I had also assumed that many of you are familiar with the main motivations behind supersymmetry. It's known that supersymmetry has the beneficial effect on a field theory of improving its ultraviolet behavior, because it makes ultraviolet divergences less severe. This is due to the fact that the contributions to loop divergences coming from bosons, bosonic and fermionic field partially cancel. Okay, so there's this beneficial effect, and this is the reason why supersymmetry was put forward as a possible solution to, for instance, the hierarchy problem in particle physics. Hierarchy problem related to the large ratio between the Planck scale and the standard model scale. Okay. Supersymmetry indeed protects the mass of the Higgs boson from dangerous quadratic ultraviolet divergences, one-loop divergences. as you all know, it also makes the renormalized coupling constant of the standard model. This in the minimal supersymmetric extension of the standard model converge if extrapolated through their renormalization group flow. Now they converge at a very high energy, okay, at an energy scale of about 10 to 16 GeV. It also provides a viable candidate for dark matter, very light particle. So, in order to connect two states with different spin statistics, the generator of supersymmetry transformations, which we denote by Q, should belong to the spin 1/2 representation of the Lorentz group, which we denote by SL2C. In particular, it should belong to this representation 1/2 0 0 1/2, which is the representation of spin 1/2 particles, as you know. So, what are this index structure, or what is the index structure of these supersymmetry generators? So, supersymmetry generators are fermionic generators, in that they carry an index alpha in this 4-dimensional representation, running from 1 to 4. This is the spinorial Majorana representation of the Lorentz group. Then we can have different amounts of supersymmetry at any dimensions. Here we are working in 4 dimensions, okay? And the number of supersymmetries is labeled by this capital index A, okay, running from 1 to n. N is the number of supersymmetries. And this index A is acted on by a compact group, which is the automorphism group of the superalgebra. It's called R-symmetry group. For the Poincaré superalgebra, that is the supersymmetric extension of the Poincaré group, this group is UN for any n up to 8, and SU8 for n equal 8. Okay? So, according to this index structure, also the parameters, okay, are the same index structure, okay, and they are Grassmann numbers. So they are anti-commuting numbers. Now, consistency of the definition in a relativistic field theory of these generators imply that they should satisfy commutation relations instead of anti-commutation relations. And in particular, in the super Poincaré algebra, which is the one which supergravity is based on, okay, the anti-commutator of two supersymmetry generator closes on space-time translations. The generator of space-time translations is denoted here by P mu. Is one of the generators of the Poincaré group. Okay. Now, an interesting from this anti-commutation relation, it follows that the commutator of two supersymmetry transformation on any field amounts to a space-time diffeomorphism, that is a space-time translation. You can see this from by inspection of the effect of a supersymmetry transformation on a bosonic or a fermionic field. The general form of the supersymmetry transformation of a bosonic field is this one here, written here. Here denoted by B, generically any bosonic field, by F, generically any fermionic field. So the variation, supersymmetry variation of a bosonic field, this is written very schematically, can be written as epsilon bar times a fermionic field. Okay, this result is a bosonic field. Okay, all spinorial indices here are contracted. Okay, and they are understood. Okay, they are suppressed. And the variation, supersymmetry variation of a fermionic field has this general form here. Okay, you see the result is a fermion indeed. Okay, and they are all proportional to the supersymmetry parameter epsilon. As we will see, there's going to be another fermion in supergravity theories, which is the gravitino. And for gravitino fields, the variation, supersymmetry variation has another term, which is the gauge variation, the transformation of the gravitino. It's a derivative of epsilon. Okay, but for the time being, let us let us consider these general expressions, and you can easily verify that if you do perform a commutator of two infinitesimal supersymmetry variation on a bosonic field, what you end up with, this is an easy exercise, you just perform two consecutive supersymmetry transformations only, you end up with a infinitesimal spacetime translation, defined by a parameter psi, which is a bilinear of the two supersymmetry parameters. Okay? So, from this it follows that invariance under local supersymmetry transformations, namely invariance under supersymmetry transformations parameterized by epsilon parameters depending on space-time, okay, implies also invariance under local space-time translations, but local space-time translations are general coordinate transformations, are diffeomorphisms, okay? And invariance under diffeomorphism is the symmetry principle underneath general relativity, okay? So this implies that a theory which is locally invariant under supersymmetry transformations must contain Einstein's theory of relativity. Now, from this heuristic argument, of course, it doesn't follow. This is just telling you that it is necessary for a locally supersymmetric theory to contain Einstein's theory of relativity. But constructing it, proving that it exists and constructing it is highly intriguing. Indeed, the very fact that Einstein's theory of relativity admits a supersymmetric extension is a non-trivial result. It was proven, it was constructed by Ferrara, Friedman, and Mielenhausen in 1976, okay, using the second-order formalism for the spin connection. And then it was derived a bit later, the same year, by Deser and Zumino, but using the first-order formalism for the connection, the spin connection. I will define what these formalisms are in a moment. Okay. So the main ingredient in a locally supersymmetric theories, which are called supergravity because they contain Einstein's gravity. They are a supersymmetric extension of Einstein's gravity, so they are called supergravity. So the main ingredient, new ingredient with respect to global supersymmetric theories is the gravitino field. The gravitino field is the gauge field associated with this new local invariance, this local supersymmetry invariance. Okay? So what are the quantum numbers of this field? We know, as for any gauge fields, okay, its indices, it should carry the indices of a generic parameter of the local symmetry. And in addition, it should also have a space-time index, because it's a connection is a one-fold. Okay, so from a space-time point of view, it has this vector index. Okay, mu. So since the generic supersymmetry generator has an index structure alpha A, okay, the gravitino field should have the same index structure alpha A, and in addition should have this index mu. Now, so in discussing, describing supergravity, okay, we are forced to describe fermion fields on a curved background.
So,
sure.
I didn't understand why there should be an additional switch index.
Yes, because you see, in ordinary gauge theories, although this is not properly a gauge theory of supersymmetry, but in ordinary gauge theory, what you do is you associate. Let me write it here. You introduce, to make the theory local, you introduce a gauge field. Okay. Now this gauge field, so you introduce a connection, basically. Okay. This connection is a one-fold. the idea is that using this connection you construct covariant derivatives. So it has to have a space-time index, because being a connection, it has to combine with ordinary derivatives so as to make a covariant derivative. Okay. Now, for supersymmetry, as we shall see, things are a bit more complicated, but the general idea is this one. And as we shall see also, even local invariance under local space-time transformations, translations, diffeomorphisms, okay, can be associated with a gauge field of this form. Okay, not of this form, but according to the same rule. And this gauge field is the gravity. So it has the same index structure as the generator of space-time translation. Okay, and in addition, it has a space-time index. This is going to be the field line field, which I'm going to introduce in the next slide. Okay, so the general rule is this one. For gauge theories, this is normal. Okay, because you associate with these local invariants a connection, and that connection has a space-time index. Okay. Okay. So since we need to describe fermions in supergravity theory on curved space-time, okay, then we have to formulate Einstein's theory, so gravitational theory, general relativity, in terms of field line, for the reason I'm going to outline here. So, just as general relativity, supergravity is defined on a pseudo-Riemannian space-time manifold with a Lorentzian signature endowed with an affine matrix, okay, which matrix connection, which I denote by gamma, okay, capital gamma. Now, the presence of fermions, as I just said, like the gravitational field, calls for the so-called tetrad or Vierbein in 4 dimensions, or in generic dimensions, Vierbein description of the matrix. Why do we need this kind of description for this kind of formulation for describing fermions in curved spacetime? Well, in flat spacetime, fermions are described as fields transforming in a specific representation, the fermionic representation, a spinorial representation of the Lorentz group, or better, of a double cover of the Lorentz group, okay, the spin. And in flat spacetime, in Minkowski spacetime, the Lorentz group is an isometry group, so it's manifest. It's axon coordinate differentials. So it's an isometry, it's a symmetry of spacetime. In a generic curved spacetime, we lose this symmetry because a generic curved spacetime may have no symmetry at all. So where is the Lorentz group that we need to define spinorial fields? How do we define this Lorentz group? The answer to this is by making reference to the local inertial frame. Okay, so by describing the matrix through the field line, to so-called field line fields. So it consists in writing at any point the matrix, which is a 4x4 matrix field. So in this way, using these matrices V mu A, okay, depending on X. Eta AB is the flat Lorentz matrix, okay, simply the diagonal matrix, plus, minus, minus, minus. Okay, so that we can do this is guaranteed by general properties of matrix theory, that we can always do this. But what is the meaning, the physical meaning of these objects, in particular of these indices A and B? The indices A and B are called rigid indices, as opposed to mu nu, which are curved indices. Rigid indices, they are associated with the so-called local inertial frame, or free-falling frame, the Einstein lift, okay, that we can define at each point in space-time. The local inertial frame is defined by a set of coordinates labeled by A or B. Okay? A set of coordinates which have the property that in these coordinates, the metric at a specific point, just at that point, is equal to eta AB. So you can choose basically a basis of the tangent space, okay, which is called the tetrad basis, on which the matrix is just eta A. But this you can do at a single point, at a specific point, at any point, okay, but not in a neighborhood of that point, just at that single point, okay, you can do that. And moreover, in this coordinate system defining the local inertial frame, also the first order derivatives of the metric vanish. But in general, the second order derivatives will not vanish if the manifold is curved at that point. Because otherwise, you will have a flat matrix at that point. Okay, but in general relativity, curvature is or maybe non-vanishing in a single point. Okay, so you can make the matrix coincide with eta at that point. You can make its first order derivative vanish at that point, but not the second order ones in general. Okay, so this coordinate frame defines the local inertial frame, the free-falling frame, where local inertial frame is very important in general relativity because it defines the relationship between general relativity and special relativity. So it allows you to define the limit within general relativity where to recover special relativity. And this you can define at each point in space-time. Okay? So, V, what's the relation between these V matrices and, oh please.
Is this why the manifold needs to be pseudo-Riemannian?
Yeah.
Okay.
The
If it was Riemannian, it would be Euclidean, right? Locally.
Look, it would be Euclidean, precisely.
Okay.
So the reason why you can make the matrix choose as a coordinate frame whose matrix has that form paired with that signature is because we are a pseudo-Riemannian. Okay, if we were Riemannian, then you could do the same thing, but with a delta instead of eta.
Right.
So plus. Okay. So you could not change. You cannot really change the signature. That's something you cannot do. Okay.
So I see you're using mostly minus signature. Is that?
I apologize for that.
For the whole lecture.
For the whole lecture is going to be like that. I really apologize for that. But, I know that there are different communities and so please forgive me. Yeah, I'm going
I
to
also use it for my particle.
You also use it
for my particle physics.
For the courses,
For my GR, though, I use
GR usually, because it somehow, in some sense, it is more natural to use the mostly plus, because you get to Euclidean or Euclidean signature when you restrict to space. Okay, so what is the relationship between this V, which are called the Wilbine field, okay, and the local inertial frame? Well, these V are nothing but the Jacobian of relating the coordinates of the local inertial frame to the generic coordinate x mu at a point. At a point. In general, in an open neighborhood of that point, V are not the Jacobian of anything. Otherwise, you would have a flat metric. Okay, so that's really good. So you can describe this. You can describe these matrices V mu A in terms of one force. You define one force. At any point, which are V mu x, V mu A x, mu or x, whatever, I suppress the index of x, dx mu. Okay, these are one form fields. Okay. Good. Sometimes in textbooks, they of course, these belong to T star x of n. That is to the, you know this notation? This is
Cotangent.
yeah, okay. But sometimes people use the corresponding dual basis in the tangent space X. Okay, the relationship between the two is VA, E, D is equal to delta E. Okay, so this means that E, A is just D, A, mu, D over dx, where dA mu is just the inverse of dA. This is what people call the tetrets, the tetrat frame. Okay. Good. So, of course, the local inertial frame is defined modulo Lorentz transformations, which act on the rigid indices. Now, these Lorentz transformations, by definition, are associated with each point in space-time. And in order to see that, you have to describe, use the theta description of the matrix. Okay, that makes local Lorentz transformations manifest. Okay, so you see, if you transform the field binding by acting on the rigid index by any Lorentz transformation, okay, then you have an equivalent description. Yes.
Is that the full O1 comma 3, or is this just connected independently and added?
Is the full?
The O1 comma 3 you have there, is that the full Lorentz group, or is it the restricted Lorentz group?
No, it's the full one. It's the full one. Yeah. In general, you see, what you can act by the full as O13, so O13, and then this is left invariant. So the description is left invariant. Okay. So anything should be invariant under such Lorentz transformations. So all quantities in general relativity should be invariant under this local Lorentz transformation, which is a local Lorentz, which is a Lorentz completely associated, I repeat, with each point in space-time. Okay? And this is a true gauge symmetry. This is the only true gauge symmetry of general relativity. So by true gauge symmetry, I mean that in mathematical language, it's a truly vertical group, okay? While space-time diffeomorphism are not true gauge transformations. The reason is that the parameters of local space-time diffeomorphisms are space-time coordinates, okay? And the dependence of the fields on space-time coordinates cannot be, the effect of a gauge transformation, because the gauge transformation do not alter physics, while in the dependence of a field on space-time coordinates there is dynamics, there is physics. Okay, so space-time coordinates are not gauge coordinates, cannot be. So that's why local space-time translations are not properly gauge transformations. They are local invariances, but they should not be considered, regarded as proper gauge transformations. These are proper gauge transformations. Okay, nothing should. The dependence on the parameters of this group, okay, is totally unphysical. It's totally unphysical. Okay, now how are spinor fields defined on spacetime? Spinor fields are fields which transform in a spinorial representation of spin 1,3, which is the double cover of SO13. At any point in time. So, in general, spinor fields transform under the symmetry group of the point. This is a general feature. Spinor fields transform under the symmetry group of the point, and SO13X is the symmetry of the point. It's related to the choice of this basis, of this tetrad basis, on the freedom we have to choose this tetrad basis, this field line basis. Okay? And nothing should depend on this. Okay? When we are going to deal with supergravity, we'll see that besides this space-time manifold, there's going to be another manifold spanned by the scalar fields. So on top of it, there is another internal manifold. The rule is always the same. The fermionic field should transform under the local symmetries of space-time, local Lorentz, and of this new manifold. But the rule is always the same. Spinors always transform under the symmetries of the point. Okay, so let us recall what the local symmetries of our theory, supergravity theory, are. So we have invariance under local supersymmetry transformations. The generators are Q alpha A, and they correspond to the gravitino fields, okay, psi mu alpha A. I will often suppress the index alpha, okay, when writing various formulae. What is the spin of the gravitino fields? Let us write the gravitino fields, by turning the curved index mu into a local Lorentz index. This I can do. Define a field like this using the field line. Using the field line, at any point I can turn alt mu into a local Lorentz index, which is a rigid index, which is associated with a well-defined representation of the Lorentz group. So what's already on? Okay. Now we can assess what the representation of this field is with respect to the local Lorentz group, because this is an index of the local Lorentz group. This is an index of the local Lorentz group. Okay, this is another index. We are not going to talk about that. Okay, so this is a spin one index times a spin 1/2 index, which is this one. Okay, so if you do the product of a spin 1 times spin 1/2, you get spin 3/2 plus to see spin 1/2. Okay? Now, elementary particles are in irreducible representations of the Poincaré group, okay? And the representation of the gravitino field is the spin 3/2. We can get rid of this spin 1/2 component by imposing the following condition: gamma A psi A, gamma A psi A equals to 0. This object here transforms in the spin 1/2 component. This contraction selects the spin 1/2 component of the gravitino field. And by setting it to 0, we are really selecting the representation of the gravitino field. Okay? So when we quantize the gravitino field, we need to impose this condition here, because we need to select the truly propagating degrees of freedom, which are the spin 3/2. Right? So the gravitino field has a spin 3/2. Then we have space-time invariance under local space-time translations. You see here what I was telling you before. The generators of space-time translations are PA, okay, and we can associate with them the field-bound field, which has two indices. This index of PA, so the same index as the generator of the local symmetry, plus a space-time and additional space-time index, according to the same rule. Okay, so gauge fields have this general index structure. Okay, the index of a generated parameter or of the infinitesimal generator plus a space-time index. Okay, and this describes the graviton spin 2 field, the graviton field. So the field-bound field describes in general relativity or supergravity the graviton field, and it has a spin 2. Then we have invariance under local Lorentz transformations, and the generators are denoted by JAD. These are true gauge transformations, as I said, and the corresponding gauge fields, okay, are nothing but the spin connection. And you see they have the same index structure as JAD, okay, but an additional space-time index, because you have to construct using them connections. So covariant derivatives. Derivatives which are covariant with respect to the local Lorentz transformations. This is a true Lorentz gauge transformation. Okay. Are you familiar with the spin connections? Do you know how they are defined? Let's define them.
Sorry, Professor. Just as a reminder, the indices A, normal script A, A's and B's, those are the ones we saw in the
On the field. These are the space, rigid space-time indices. These are the indices labeling the local inertial frame. Yeah. So they are defined modulo local Lorentz transformations. So local Lorentz transformation act on AB. They don't act on B.
So one more thing about these indices is that before imposing the supersymmetry, like for example, if A is under local supersymmetry, our alpha index is downstairs and A is upstairs. And after it, same. But when we do invariance under local space-time translations, then the rigid index goes upstairs. And same
Yes. The position of the A index.
Yeah,
That's not relevant because you see, why the position of alpha, that's important. The position of the A and B indices is not really important because you can raise them or lower them using eta AB. So using the Lorentz, the flat Lorentz metric. So the position of A and B is not really important. You can define the position of the mu index is important. Okay, that you can change by contracting with the matrix, space-time matrix, G mu or its inverse. But as for the rigid space-time index, well, this is nothing but eta AB BB. Okay, so it's just changing the space components by a sign. So how is the spin connection defined? So we have defined on our manifold a metric affine connection. So we have a metric affine connection. Metric affine connection. Let us denote by gamma the connection symbol. Okay, this allows us to define covariant derivatives. Okay, so and we have our symbol and we have our field line, local field line at any point. Okay, now we can apply the covariant derivative defined in terms of gamma to the mu A. That we can do. Okay, how is this defined? Well, this is d mu v mu A minus gamma mu rho v rho A. Okay, this is the definition. Now I call this minus omega A B mu v mu. So I call this action this. So I define omega through this action. The effect, the result of this action here, okay, I write it in this way. And this defines our spin connection.
Is there a comma there after B?
After B, yes, there is a vertical line just to distinguish between these two indices, okay, otherwise it tend to mix. Okay, so this is the main structure. This is our spin connection, okay, and you see it's contracted with V, okay, through its rigid index, second rigid index, okay, so it acts on the second rigid index. So that we can define a weak covariant derivative, okay, mu of VA mu, which is plus omega A mu VB mu. We define this like this. This is a definition. Okay, if we define the covariant derivative like this, then we see this is 0. But it's 0 because I define omega like this, so it's trivial. But this is the so-called first field bind postulate. Okay, first field bind postulate. So the covariant derivative of the field bind, okay, covariant with respect to the space-time translation and the local Lorentz transformations, okay, is 0. Okay. Now omega is the connection associated with local Lorentz transformations because it has to, you see, if I perform a local Lorentz transformation with parameters which depend on space-time, because local Lorentz transformations do depend on space-time, they are defined at each point in space-time, then this is covariant provided omega transforms correspondingly as a connection. Okay, so omega is the connection which makes this derivative covariant also with respect to local Lorentz transformations. And I suggest you to do this as an exercise. Work out the transformation properties of omega so that D, defined like this, is invariant under local Lorentz transformations. Let's write it here. Exercise. Determine transformation properties of omega under local Lorentz transformations lambda AB X in SO or O13. Okay?
I have like a very basic question. So we are defining, like we are saying that omega is a connection on the locally flat metric, right?
Yeah.
But isn't the connection on locally flat metric 0?
No. It's a connection not. It's not associated with it. It's a metric connection. That is, it leaves the metric, the flat metric invariant. So this, the fact that omega is a metric connection means that this connection leaves eta AB invariant. Okay, basically it has to be invariant. Okay, but omega is not the connection associated with this metric. Okay, omega is the connection associated with local Lorentz transformations. So it cannot be defined in terms of eta as you would define a gamma as a Levi-Civita. Okay, omega AB seen as a one form. Okay, is in the local Lorentz group because of this condition here. So this means that if I act on this by eta, okay, this must leave eta invariant. The action of omega must leave eta invariant. Okay, this is what you get from here. But this is amount to saying that this is equal to minus omega CB eta BA. Okay, omega AD belongs to the algebra SO1,3. The Lorentz algebra. It acting on eta leaves it invariant. Okay? This follows from here, from this one. Eta has to be invariant. The constant. Okay? So this is the exercise, it's a useful exercise. Okay? You will see that delta omega prime should be lambda minus 1 omega lambda plus lambda d lambda. I suppress all indices. Okay? Lambda minus 1 d lambda. So it has to transform as a connection. And you have to verify this. Okay? Okay. So the second two are manifest in supergravity and general relativity in general. The first two are manifest simply by defining an appropriate covariant derivatives covariant derivative which contains the affine connection, matrix affine connection, gamma, okay, which is torsionless. So we take the Levy symbol, okay, omega, and the torsion is in omega. All torsion is in omega, plus possibly other terms associated with local invariances, which we are going to introduce in the next lectures. Okay, we are going to introduce, for instance, here. Oh, what happened? I have to press.
Yes.
Yeah. Okay. Okay. Fine. Thanks. So we are going to introduce local Lorentz invariances. Not local invariances. Local internal invariances. Okay, gauged by the vector fields, and then we will need to add an extra connection. This time depending on the vector fields. This is implied by the gauging procedure, but we are going to discuss about this. Okay, so far this is the structure of the covariant derivative that we will use. All torsion is in omega, as we are going to see in supergravity theories. There's going to be torsion. Okay, so the gravitino field. Let's spend a few words about the gravitino field and its description, dynamical description. So the gravitino is a massless spin 3/2 field, as we said. Its dynamics is described by the so-called Rarita-Schwinger equation, which is an equation that was found by Rarita and Schwinger in 1941, so a lot of time ago. And it has this form here in flat space-time. Okay, so it's a kind of generalization of the Dirac equation, but for spin 3/2 fields. Okay, gamma mu are the usual, defined usual Clifford algebra. And you see that this equation has this invariance, has this local invariance. So it's invariant if we transform sine u by the addition of a derivative of some spin 1/2 field. Okay, so local spin 1/2 parameter. So this is a local symmetry associated with the spin 1/2 parameter. This is a supersymmetry. Okay, and you see, in flat space-time, there's no problem, because if you vary psi this way, okay, we have two partial derivatives whose indices are anti-symmetrized, so it's 0. And this is what you need, in fact, to define a massless spin 3/2 field. As for all massless fields, you need to decouple the longitudinal modes, which are ghost modes. They are unphysical. So you need to decouple, just as for the spin 1 electromagnetic field, A mu. Okay, and this is guaranteed by the gauge invariance. Okay, so this unphysical component you can dispose of by gauge fixing. It's just unphysical. It just does not have any physical implication, and you can just gauge fix it. The same is true for the gravitino field. The gravitino field is a massless spin 3/2 field. Okay, and let's not update it now. Okay. And so it has an unphysical longitudinal component, which is described by a spin 1/2 field. Okay, and this is telling us that this spin 1/2 field is unphysical, so it will not enter the dynamics. Okay,
Professor. So there's this floating uncontracted index in the.
Yes.
The
mu index.
The mu, yeah.
Yeah, the reason is that in fact there are two floating indices. One is mu, and another one is hidden, because I wrote them implicitly. I just suppressed all Lorentz indices. Sorry, all spinorial indices. But there is a floating spinorial index there in gamma. The reason is that you derive, as we will see in this equation, by varying an action, which is Lorentz invariant, with respect to the gravitino field. So you're varying something which is Lorentz invariant with respect to the gravitino field. So the field equation must have as many free indices as the gravitino field. Because you're deriving this, you see, by varying some Lorentz invariant action with respect to the gravitino field. So the free indices will be mu and alpha. Mu and alpha that you will see, which is the raw index of the gamma matrix. Okay.
So there would be two indices there, one of which has been contracted with the fields, and then the other one's
two indices in gamma, one is contracted with psi.
With psi.
Yeah, it's useful to write them in indices. So let me write it.
Yeah, sorry, I suppose all these index contractions are familiar, but not all together all at once. So
I know. Too many indices can
keep track
be
of
harmful. Yes.
different things that are going on.
No, of course, that when one is not familiar with this notation, then okay. Then you have gamma, mu, alpha, beta, and then here you have beta. Let's write it like this: psi, rho, beta. Okay. No, in fact, it's d rho, psi, sigma, beta. Okay, this is the written in explicit indices. You see, the three indices are alpha and mu.
Yeah.
Because this is going to follow from delta S over delta psi alpha mu. And you see it's going to be alpha and mu, three indices. Okay. Now we're going to do that. Okay. So in order to describe in a consistent way a massless spin-free half field, this has to be associated with a gauge device, okay, which is needed to decouple the unphysical components. Okay, the gauge components. Now, in curved space-time, the equation simply generalizes in this way by replacing ordinary derivative by covariant derivative, the same covariant derivative I discussed, I defined in the previous slide. You see, and you can write this equation in an equivalent way. Okay. Now, consistency would require that the unphysical longitudinal components, as we said, okay, decouple in curved spacetime as well. However, if we covariantize the gauge transformation, the above gauge transformation by replacing ordinary derivatives by covariant derivatives, this is the only way to covariantize it. Okay, you see that this is no longer a symmetry of the equation. Because while this was a symmetry of the Rayleigh-Schwinger equation, because you see, ordinary partial derivatives commute. Covariant derivatives do not commute. They do not commute. And in fact, you have that d mu acting on some field phi, whatever, is nothing but the Riemann curvature tensor acting on the same phi, okay? The Riemann curvature tensor acting on the same field phi, inappropriate. Plus, if we have other internal symmetries, okay, then there will be other curvatures here. But for the time being, this is the main. You can verify this equation. Just check, just compute d mu on psi rho acting on psi rho. Okay? With this exercise, you will find the Riemann tensor, okay, acting on all the indices of this guy. There are two indices, one which is suppressed, which I suppressed, okay? And you find the curvature acting on all the indices. So we find SJA is equal to 1/4, sorry, gamma, or better, 1/4 gamma A, gamma B, anti-common. You can verify that this is the spinorial representation of the Lorentz generator JAB. So this is the way this is the commutator of two covariant derivative on a field is R in a suitable representation of the field, acting on the field. Okay, this action on space-time indices is this, and the action on local Lorentz spinorial indices is like this. Okay, so you see they don't move. Yes.
Maybe it's worth, maybe you said it, but it's worth emphasizing that R mu there is not the rigid tensor, because it just looks a little...
Oh, I'm sorry. No, it's not the rigid tensor. No.
You're just not specifying the other two components of it.
Yeah, I cannot specify the other two components. Thank you. It's not, this is the Riemann tensor. This is the Riemann tensor. Okay? This is the Riemann tensor. Just to make
Just because maybe it's confusing if people see it.
No, I totally agree with you. I mean,
sorry, I know some of this is
yeah.
basic, but just to avoid...
No, it's important. It's important. R, the Riemann tensor, no, as a function of the affine connection, mu rho sigma, that you can find like d mu gamma mu rho sigma minus d mu gamma mu rho sigma and plus blah blah blah. Then there are other terms, okay? But now you can turn these indices. So you split these indices in the first couple, which is anti-symmetric, and in the second couple. Okay. Now this is the if you want this second couple, define the action on the vector fields on the tangent space. Okay. The second couple. Second couple define a linear action on the vector fields on the tangent space. Right, so if you have a vector field on a tangent space, you know how to run the path, okay? It rotates. And you can also write this A. You can verify that these two are just the same. How do you verify this? Using the field binding postulate. Okay? D mu V mu A is equal to 0. You do two derivatives and you anticommute them, you get that this has to be 0, but the commutator of these two covariant derivatives is expressed as the sum of two acting on this and this. Since it has to be 0, these two are equal. Okay? So instead of writing the Riemann tensor in terms of gamma, okay, where this is the torsion for gamma, this is the torsion for gamma, it's much more convenient to write the Riemann tensor in this way, using the spin connection. So this is the curvature associated with this gauge field, the spin connection.
So that's kind of like you normally see the field strength if you knew a period.
Precisely. You have a gauge field and you define the field strength, like in electromagnetism. Here we have a gauge field, omega, AB. AB are the internal indices. They are true internal indices, AB, okay, associated with the parameter, the gauge parameter. and you have an index mu, and then you associate a field strength. This is the field strength. Okay? So this is really a gauge field strength. The field strength associated with the gauge field. The gauge field is on. It's a true gauge field.
So when we took that commutator of the covariant derivatives there, we got two terms, I think on the other board, we got two terms, the ones associated to curvature of space-time and the others associated to the gauge, the kind of field strength.
Precisely. And the result has to be zero, so let's do it. The result has to be zero. So this is all in my notes, by the way. D mu, V rho, A. Using the formula here, we have to act by means of this R on all indices. This is R, gamma, rho, sigma, gamma, V, rho A, okay, sigma A, sorry, plus, I have to act on A. But the action on A is defined by this guy here. AB, and this has to be zero. So here you get the relation between the two. They are the same. If you want, you can do the explicit computation. That's a bit lengthy, but you get the same result. Both are in the if you want, they are all on the lecture notes.
I was just thinking maybe this is a good point to have a little break for coffee.
Sure. Okay, good. Let's have a break.